Hello everybody. In this chapter we're learning a little bit about the patterns that you can see on the periodic table and how they relate to atomic structure and things like electronegativity, ionization energy, some of those topics that you learned about in Honors Chem. Before we start talking about those patterns again, I want to do a lesson on the reasons why we end up seeing those patterns. So we're going to talk a little bit about shielding and some other things that will be the cause, the reason for the patterns that we see on the periodic table. When we're trying to describe and explain the patterns we see, everything is going to come down to two things. It's going to come down to attractions and repulsions. We're either going to be referencing how the electrons are attracted to the nucleus, or we're going to be talking about how the electrons are repelled by each other. And all sorts of patterns can be explained by one or both of these things. So if you remember from Honors Chem, shielding is what happens when the inside electrons prevent the valence ones on the outside from feeling the full effect of the nucleus. Remember this little cartoon? I love this cartoon. They're basically providing a buffer, a shield, or a screen so that they're not pulled in to the nucleus as strong. The electrons that are in the same energy level don't really shield each other very well. So if you have some valence electrons in energy level 4, for example, an extra electron added there, they don't shield each other very much. This is really talking about core electrons versus the valence electrons. You may hear the word screen, so I just want to make sure that, when you are doing practice, if you see the word screen, you understand it's the same thing as shielding. Another term that should seem familiar to you is effective nuclear charge. Remember, the nuclear charge, the number of protons, may not be what that valence electron is feeling. It may not be the relative strength that that electron experiences. We have ways to calculate the effective charge, the effective strength of that nucleus on the electron. We use a very, very simplified one in this level. Z is the nuclear charge. S is the number of electrons in all those lower energy levels. Remember, we're not going to count the ones in that valence shell because they don't really shield each other, right? Because they're in the same energy level. In real life, the equation for this is a little bit more complicated. We would use something called Slater rules. The nice thing is we don't have to learn those. Those are mathematically calculating a little more correctly based on the fact that not every type of orbital, not every orbital shape shields to the same degree. So it's just trying to calculate a more accurate effective charge. But this, good enough for what we're doing. One thing you should know though, just conceptually, even though we don't have to do the math of it, is that s orbitals shield the best. And then p orbitals, and then d orbitals, and then f orbitals at the very end. And this has to do a lot with their shape and how they're distributed amongst, the atom. And so understanding that s orbitals shield more effectively is important. This will help explain why sometimes it's easier or harder to remove electrons than we might anticipate, because they may be experiencing more or less shielding than you would expect. Here's a picture that tries to show this effective nuclear charge a little bit. If you see here, we have a nucleus with 3 protons, and we have some inner electrons here. And then out here, we have our valence electron in the second energy level. Now this valence electron is not feeling a pull of 3 from the nucleus because these electrons are providing the shield, the screen, the buffer for this one. So these are repelling each other a little bit, right? And they're in the way between the valence and the nucleus. So instead of this valence electron feeling a tug of 3 inwards, it's really only feeling a 1. We subtract out those core electrons. So instead of a 3 plus charge, it feels a plus 1 charge. Another thing that we did not talk about in honors chem is something called penetration. And this is what happens when an electron might be closer to the nucleus than you would expect. Remember that our orbitals have different shapes, and also that our orbitals are not necessarily where we are guaranteed to find our electron, right? Remember, these are areas of probability. We are most likely going to find an electron in a certain area. Well, some types of orbitals will result in the electron being closer to the nucleus sometimes than that outer edge that we see. So if you look here, here's this outside electron, and it's hanging out over here. But once in a while, we may find it closer to the nucleus in here. And when it penetrates inwards, it will feel a stronger pull from that nucleus because it won't experience the shielding as much as when it's out here on the outside. So this electron coming in further than expected is penetration. Remember, we can draw a graph showing the probability of finding our electron and how far away from the nucleus we are. Remember, we draw our orbitals not as tangible objects, but they're really a map of everywhere mathematically we think we'll find an electron, as if you put little dots on your paper over and over and over everywhere you think you'll find one. Doesn't mean the electron can't be closer to the nucleus than the outside. An interesting thing that you find when they start doing the quantum mechanics of all of this, all the crazy fancy math, is they find that as you start getting larger and larger s orbitals, you start having regions of space where you have low zero probability of finding that electron. So we end up, as you can see here, in a 2s orbital. This area we're not really going to find an electron, but we could find an electron pretty close to the nucleus, even though this is a 2s orbital. It's not that the electron is only out here. It could be closer. The 3s has 2 nodes here. So it's not that the electron can only be out here. It could be closer here, or it could be really close to the nucleus. This results in there being a little more attraction between the valence electron and the nucleus than you might expect, because that electron can penetrate inwards and feel a stronger attraction. We'll often see it graphed like this, and you can use the shape of this graph to figure out which orbital it is. You can see here, these peaks are much smaller than this peak. This is the most likely place we would find the electron, but we could find it in here and a little bit closer even here as it's penetrating towards the nucleus. When you look at this graph, you should be able to guess that this is going to be a 3s orbital. And which areas on this graph do you think are the nodes, the areas where we don't have any probability of finding that electron? Right there and right there. Sometimes you may see these all graphed kind of on top of each other. You may see the graph for the 1s and the 2s and the 3s all at the same time. I like those graphs because you can kind of see them compared to each other. So if we look here in purple, that's the 1s. And you can see that the likelihood of finding your electron is very high, very close to the nucleus, which makes sense. It's a small orbital. Then in green, we have the 2s. You can see that it's most likely going to be further from the nucleus, but it penetrates a little bit, and you do have some region in here where you could find your electron. And when you see the 3s, right, it's most likely going to be even further from the nucleus, but it penetrates into the 2s orbital and then again into the 1s orbital. So if we think about the attraction between our nucleus and our electrons, the closer that electron is to your nucleus, the more attraction it's going to experience. Therefore, if your valence electron is good at penetrating, then it will have more attraction than you might expect for that nucleus. And remember, those graphs, we're graphing what we call the radial distribution function, basically showing you the probability of finding your electron. So you can explain some of the trends and some of the patterns that you see, and some of the things that break our very generic patterns, some of the exceptions that we see based on the amount of penetration compared to the shielding that's taking place. So if you look in red, we have our 2s orbital, and it's penetrating inwards. Our p orbital is here, but can you see how the red line comes further in? We have more probability of finding that electron in here close to the nucleus than the 2p one does. That means that those p orbital electrons are experiencing less attraction to the nucleus. And they're going to have more shielding, aren't they? This penetration here shields a little bit. So we end up in a situation where the 2s ends up with more attractive forces to that nucleus than the 2p does. And when you think about things like removing electrons from orbitals, right, the degree of ease or difficulty of that would be connected to how much attractive force there is. So you can use these types of graphs and these concepts to explain that. Here's just showing again another one. The more penetration we have, the more attraction we have, and the more shielding that those specific orbitals would contribute to the valence shell. This graph shows you the S, and then it shows you in black the P, and then in red it shows you the 3D. And you can see if you look carefully down here, your blue line has a little peak, little area of probability closest to that nucleus. Now, some things to caution you about when you're giving explanations about shielding and things like that. You have to be incredibly careful with your phrasing. The more you talk, the more likely you are to start saying things that are wrong. The other thing we see is that people know what they're talking about in their head, but they're not being very explicit with their writing. So a couple of suggestions. Do not use generic or non-specific terms. I do not want to hear you saying, oh, it's shielded more. Okay, what's shielded more? Use the actual names of the atoms, okay? Be specific. Say something like, calcium's valence electrons experience more shielding. That would be better. Instead of saying it, we use the actual name. One of the things they are very picky about, that they will often attach points to, is that you must reference both of the atoms being compared. So it would not be good to say calcium's valence electrons experience more shielding. It would be better to say something like, calcium's valence electrons experience more shielding than sodium's valence electrons. I was specific. I didn't use words like it, right? But then I made sure that I am using the word than. I am actually comparing two specific things. They're very picky about that. Even if everybody knows what you mean, right? You have to explicitly say the second element you're referring to. Now, typically, even that's not good enough. So the other thing that's really important is that you have to give reasons. You have to actually explain or justify. They'll use some keyword like that, okay? So saying calcium's valence electrons experience more shielding than sodium's valence electrons, that's a true statement, but it doesn't at all explain why. There's no scientific principle that you're giving to justify your statement. So you would want to say something like, calcium's valence electrons experience more shielding than sodium's valence electrons because calcium's valence electrons are in energy level 4, while sodium's are in energy level 3. Therefore, calcium's valence electrons are shielded from 3 levels of core electrons, while sodium's are shielded from only 2 levels. That's a lot, right? But if you think about it, it kind of hits all the key points, doesn't it? We use specific terms. We didn't use things like it. We actually used the word than. We compared the two things explicitly, calcium versus sodium. And then I gave a reasoning for that. And I didn't just say something like calcium has more levels. I was very clear. I listed which energy levels. I showed you by listing calcium's versus sodium's that there was more for calcium, right? So you have to be very explicit. Honestly, I kind of hate grading FRQs for this chapter because people are trying to do such a good job that they're trying to write more and more and more and more and more. But as I've mentioned earlier in the year, you have to be careful with that because if you start to kind of go off track, you can get in trouble and start losing points, okay? So last few suggestions. Be succinct, right? Don't ramble. I am totally fine with bullet points. So is AP College Board. I always say you don't need complete sentences, but you need complete thoughts. You can use words like therefore, you could draw like arrows, you can do things like that as long as it's clear. The other thing I suggest you keep in mind is what the grading rubric is going to be structured like. What are the key things we are always looking to check off? When I look at a grading rubric, it's out of 1 point, 2 point, 3 points. If you were to imagine it's out of 3 points, what would those 3 check marks be given for? And then the next one, do not vocab drop. You cannot just say because of shielding, because of greater effective nuclear charge. That's a vocab term. That is not a reason. That is not an explanation. Okay, you should be able to explain things, not just vocab drop. It's not that you shouldn't use those terms, but you shouldn't stop at just using those terms. You could earn full points without ever using the word shielding. You could earn full points without ever using the word effective nuclear charge. But you may not, and you probably won't earn points if those are all you say. And then the best thing I can suggest is that you look at as many actual AP Chem rubrics as possible, right? You have access to the internet. You are so lucky compared to previous generations in this class, right? Look at the rubrics, read how they phrase their answers, and look at how those points are broken up. And what I want you to do is internalize their phrasing, not memorize, right? You don't want to be a robot just parroting back something, because if they throw a twist at you, right, you may end up writing down the wrong thing. But if you internalize how they're phrasing things and you start to recognize patterns and common things they're looking for, it's really going to help you for this chapter, okay? And then lastly, the reason this is so important is because these are the things that explain our trends. When we're talking about our Zeph, when we're talking about our radius and our ionization and our electronegativity and all of the weird exceptions you might see, it's always coming back to these ideas, okay? So when you get a question that's asking you something about atomic structure, something about periodicity and trends and patterns, you should have these ideas, set off in your head. You should be thinking instantly attractions, repulsions, shielding, penetration, things like that, okay? All right, everybody, I hope that was helpful. Bye.